Alright, so in this video we're going to look at infinite series. And before we can jump into the series part of this, I'm going to do a little bit of a review of sequences. If you already are familiar with arithmetic, geometric, harmonic sequences, know about their recursive definition, all that stuff, look in the description. You can skip on down to the series part. But for those that are a little bit sketchy on that, I'll go through this first. So first thing, what is a sequence? I'll define the sequence as an ordered list of, and I'm going to put numbers in here. It doesn't need to be numbers. Okay. For sequences, the elements are the numbers in the list. And the indices, or the index would be the, I believe ECES, maybe an I here. Anyway, this is the location in the list. Now, for a sequence, it's important that there is an order to them. Sets are unordered lists. Sequences have an order. So as an example, the set or the sequence of positive odd numbers, 1, 3, 5, 7, 9, and so forth and so on. In this one, the terms are like 1 and 3. The elements, terms and elements, are somewhat interchangeable. And so I could say the first term is equal to 1. The second term is equal to 3. The term at index 4, is 1, 2, 3, 7. And that's the basics of sequences in general. Now we'll look at three important sequences that show up in mathematics and talk about them more specifically. First one, arithmetic sequence. An arithmetic sequence is a sequence where, in order to get to the next term, we add the common difference which we will denote by the variable d. Now, two ways to define this. One is this. If I want to get to the next term, so the n plus first term, that will be the term that we're currently on, the nth term, plus the common difference d. In our example, 1, 3, 5, 7, 9, the first term is 1. The common difference is 2. It's an arithmetic sequence. And what this means here is, if I want to get to the fifth term, so let me write this down, t sub 5, that's going to be the fourth term plus the common difference. The fourth term is 7. The common difference is 2, so 7 plus 2 gets me the 9. And this is a common way for people to think about them. This is what this notation t sub n plus 1 t sub n means. But it's not very useful if I want to get to a very large indexed term, very far down the list, because I don't want to have to, let's say, add the common difference 1,000 times. So we also, so here's the recursive, we also have a sort of a closed form for this, saying that to get to the nth term, I'll take the first term and add on the common difference n minus 1 times. And the idea is, if I want to get to the 100th term, I need to add on d 99 times. Get first to the second term, I add d once. First to the third term, I add d twice. So that's why I'm adding d n minus 1 times. Here's an example. Given an arithmetic sequence with term 1 equal to 6 and the common difference 5, list the first 5 terms of the sequence, the general term, and the 100th term. So the first 5 terms, well, we have 6, add on 6, get 11, add on 5, get 11, add on 5, get 16, add on 5, get 21, and add on 5, get 26. That's the first 5 terms. The general term, I can use that closed form, saying, okay, if I want to get to the nth term, so this is t1, t2, the nth term is going to be 6 plus 5 times n minus 1. I could even distribute the 5 and get a slightly nicer looking format, but this will work. Okay? So this will be useful. This general term will be useful when we start doing series and get into Taylor and Maclaurin series later on, is trying to figure out what this is. And finally, find the 100th term. Well, the 100th term will be the first term plus the common difference 99, so 100 minus 1 times. The first term is 6, the common difference is 5, and 100 minus 1 is 99. 5 times 99, well, 5 times 100 is 500. 5 fewer than 100 is 495, so this is 6 plus 495, which is 501. Another common sequence, the geometric sequence. In this sequence, you get, so to get to the next term, instead of adding the common difference, you multiply by the common ratio r. So the recursive definition, t sub n plus 1, the n plus first term, will equal the nth term, the previous term, times r. And I'm not going to show an example of this right now. We'll see an example in a second, but same idea. This means the term we're on right now, I multiply the ratio to it, I get to the next term. And as before, this is great to see how something works, like 1, 2, 4, 8, 16. You see I'm multiplying by 2. But I wouldn't want to have to multiply by 2 100 times to get the 101st term. So a closed form of that, oh, don't cross it off, just underline it, is this. To get to the nth term, I will take the first term and multiply by r n minus 1 times. Notice this n minus 1 is an exponent because if I multiply by r times r is r squared, r times r is r cubed. When I multiply by r repeatedly, I get an exponent. Just like if I add repeatedly, I get a product. So that's worth noticing. And here's an example of that. Given a geometric sequence with t1 equal to 6 and r equal to negative 2/3, list the first 3 terms and the general term, there should be a space in here, I'm just going to go with it, of the sequence. So the first term is 6. 6 times negative 2/3 is negative 12/3, which is negative 4. Negative 4 times negative 2/3 is a positive 8/3. That does not reduce. And this is actually going to be super important for Taylor and Maclaurin series, this general term. So I start off with 6, and I multiply by negative 2/3 to the n minus 1. That's the general term of this sequence. And we'll need to do that later on in sort of this unit's worth of material. Okay, one more sequence to deal with, the harmonic sequence. And that's just the sequence of basically 1 over n. So the sequence 1, 1/2, 1/3, 1/4, 1/5. And I get sort of harmonic sequences by multiplying through, distributing through something, but still be harmonic. I'm not going to show an example because this is the harmonic sequence, but it is important when we start talking about the convergence of these sequences later on. Now that we've gone through sequences, we can talk about series. And a series is basically the infinite, let me say it this way, the sum of infinitely many terms in a sequence. Series is sometimes called infinite series. The sequence is the list of elements. The series is what happens when I add up all those elements. Now, a notational way to do that is I can say S is equal to the sum as n goes from 1 to infinity of t sub n. This is sigma notation, sigma for sum. That's not an E. Don't tell me it's an E. It's the closest sort of correlation is an S for sum. And if you don't know, this notation means I start n equal to 1 and I go up, I increase n by 1 each term. So this basically does t1 and I put in a 2 plus t2 and I put in a 3 plus t3, put in a 4, all the way up to, in this case, infinity. Now, you can't actually go through and add each of these infinitely many things. It would take infinite amount of time to add, let's just say 1 plus 1/2 plus 1/4 plus 1/8. So there's got to be some idea how to get here. And what we're going to do is look at partial sums. So instead of adding the infinitely many terms that we have, we can say that S sub k, the partial sum, that's not where I want that to be. That's not a k. There we go. S sub k is going to be the sum as n goes from 1 up to some stopping point k of t sub n. So that's going to be put in the 1 plus put in the 2 plus put in the 3 all the way up to the kth term. Quick example. If I have S sub 6, that will be the sum as n goes from 1 to 6 of t sub n, which will be the first term, plus the second term, plus the third term, plus the fourth term, plus the fifth term, plus the sixth term. One last thing to talk about for this, tying these together. The series, or the infinite series, or infinite sum, will equal the limit as k goes to infinity, the limit as the stopping point goes up to infinity of the partial sum. And if this exists and is finite, then it converges. If this either does not exist or is infinite, then it diverges. So here's an example. We can see the pattern. Now, I didn't give you the general term. We're going to have to find this. But I don't know what this add up is. Notice there's this ellipsis at the end. It keeps going. So what I can end up doing is actually trying to find the partial sums and see what they approach. So the first thing to look at here is to say, okay, what's the pattern? And I see 1, 1/4, 1/9, 1/16. And I say, okay, hold on, I think I'm going to have a 1 over 25 and a 1 over 36, because this is really 1 over 1. So it looks like my general term, let me put that down, of the sequence is going to be, I have a 1 over n squared. There's another problem though. Notice I'm subtracting and then adding, then subtracting and adding. So it's not going to be 1 over n squared. How do I get the positive and negative? Well, I just put a negative 1 to an exponent. Now, I'm going to put this to the exponent n minus 1. The reason being, if n is 1 here, I want it to be positive. 1 minus 1 is 0, negative 1 to the 0 is positive 1. In here, I want it to be negative. This is where the index is 2, where n is 2. And 2 minus 1 is 1, negative 1 to the first is negative 1, so it makes it negative. And then so forth and so on. The index is 3, 3 minus 1 is 2, negative 1 squared is positive. And so I can see that my partial sum will equal the sum as n goes from 1 to whatever this k is of this general term. That's why these general terms are so important. So the general term is negative 1 to the n minus 1 over n squared. And I can just make a little table and see what happens as we approach infinity. That's the best I have for this. So I'll make a table k and s sub k, and I'm just going to try a few things. So I'll try k equal to 5, k equal to 10, and I'll jump up to k equals, I'll do 50, and I'll do 100. That should actually be enough for this to settle down. Depending on how quickly the sum converges, I might need to go further. I'm going to use a TI-83 to show this. Some of the newer calculators are better and faster at evaluating it. Some of the old ones take a long time or may time out. So it shouldn't be a problem if you're doing this in a class. The teacher will probably make the problems if you need to do this so that it can be done in your calculator. But just know that it can sometimes take a while to do this. So I want to find this sum. In order to do this sum, what I need to do is I will do the sum, which is in list math 5, of the sequence, so that's list operations sequence. I'm going to use n's instead of, I'm going to use n's in here. So I could use x's to be easy, but I'll use n's. So I have negative 1 to the, let's see, n minus 1 divided by n squared. So I put in the function, I put in the variable, and I put in the starting value, and in this case the stopping value is going to be 5. Now, TI-83s and the older Texas Instruments calculators are kind of tricky notation. In some of the old Casios, I think you just sort of put the sum, and you use x's, you don't put this extra variable in here. The newer Casios, newer TI calculators, it's beautiful. You basically type this in and it works. But here we go. I get about 0.838. Let me put that down. So 0.839 approximately. Okay, but I want to see what's happening. So let me go so second entry, and I'll put in 10 instead of 5, and let's see what happens. Okay, well it's different, and it's very noticeably different. So 0.818. Actually, those decimal points show up. And I keep going. So clearly I don't have the answer yet. I don't have nearly enough information. Let's go up to 50. So second entry and change it to a 50 and see if it's still changing. Takes longer. Okay, it changed a little bit, but notice not as much as it did before, 0.822. But if I'm sort of AP calculus style trying to get 3 decimal places, notice that the 3 decimal places have changed. They haven't settled down yet, so I'm not there yet. Let's see if it works to 100. So 100. When I put this in, I see I'm still at 0.822. I did not change. I am reasonably confident that that is accurate to 3 decimal places. If I wanted to, I'm not going to right now, I could go up to, let's say, 200 and see that, okay, it has settled down, this is my sum. It converges to this value. Last thing, geometric series, which are, again, critically important for a lot of our later series in calculus. And there's a trick to it. So the sum of an infinite geometric series is going to be this, and I'll explain why. It's going to be the first term divided by 1 minus r. And here's why. So in a geometric series, we know that we have, so let me say because, we have this. The sum is going to be the first term plus the first term times r plus the first term times r squared plus the first term times r cubed plus ellipses. Dot, 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 whatever. Okay, because I keep on multiplying by r to get to the following terms in this sequence. If I multiply this by r, so I have s times r, basically what that does is that transfers each of these over. So I will have, instead of having t1, now I have t1 times r. It distributes to everything. And instead of having t1r, I have t1r squared. Instead of t1r squared, I have t1r cubed. And instead of having t1r cubed, I have t1r to the fourth. Now there's an important thing, I forgot to write it here. R has to be between -1 and 1. Okay, the common ratio has to have a magnitude less than 1. And what that does for me is this. If r's magnitude is less than 1, these terms approach 0, so out at the end, they make no difference. The fact that there's sort of this extra term hanging out here, well, it's approaching 0 anyway. And so when I subtract these, I'll end up getting s minus sr equals t1. Those cancel, those cancel, those cancel, this will cancel, and since the terms are going to 0 when I cube or when I put a small magnitude number to a high exponent, there is no sort of junk left over. It does converge. And then to solve for s, I'll factor out s, 1 minus r, divide by 1 minus r, and bingo bango, we get that formula. So whenever I see a geometric series, I can know right away if it converges. So let me put it in a little box. If the magnitude of r is greater than or equal to 1, the series will diverge. There's a special, like if you have the zero sequence where it's all zeros. But other than that, it diverges because I'll be adding larger and larger values. So 2 examples this time. First example here. We'll evaluate this. 1 plus 2 plus 4. And if I'm not thinking right, I can start doing some work and say, okay, t1 equals 1, r equals 2. Should be a red flag right now. This is not inside our possible range, so it diverges. Now, if you take a second and think, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 is going to explode larger and larger and larger, go to infinity, and clearly it'll diverge. But here's what I see. Make sure you don't get stuck just saying, okay, put 1 over 1 minus 2. No. Diverges. This formula only applies when r is between -1 and 1. Now that was kind of a chump out example. Let's see one that actually converges. So here we go. In this case, the first term is equal to 1. The common ratio, well, a way to get a common ratio is to take a term and divide it by the previous term. So that's -1/2. If you're ever having trouble finding it, -1/8 divided by 1/4 is still -1/2. So if you know it's geometric, you're not sure what common ratio is, take 2 consecutive terms and divide them. This is between, so I'll mark that here, is between -1 and 1, so I can use the formula, so the infinite sum will equal t1 over 1 minus r, 1 minus negative 1/2, well, 1 is 2 halves, plus 1/2 is 3 halves, so I have 1 divided by 3 halves, and when I divide by a fraction, that's the same as multiplying by its reciprocal, and I get 2/3. And if you don't believe me, okay, let's just say you don't believe me here, I can actually go to the calculator, and I can do the sum of the sequence. And for this one, the sequence will be negative 1/2 to the, and I'll be lazy with this, x minus 1, comma x, comma 1, and let's go up to the 100th term. Okay, let's do the same thing. It adds them all up, takes a little time, wastes some of our time, wish I had a faster calculator, and 2/3. Okay, rounded off to the 10th decimal place. Alright, I hope that helped. Feel free to comment below with any questions, and next video we'll get into how to know when these series converge or diverge without having to actually evaluate them.